Eric Burgess here. Test the claim that the standard deviation of the number of aircraft stolen each year in the United States is less than 13 if a sample of 10 years had a standard deviation of 14. Use the 0.05 level of significance. Alright, so our first step is going to be identifying the null and alternative hypothesis in the claim. So let's go ahead and write those down. We're going to have a null hypothesis, we're going to have an alternative hypothesis, and we want to find the claim. So let us do this. So it says up here that the claim, well, it tells us the claim right at the beginning, that the standard deviation of the number of aircraft is less than 13. And so we say, okay, well, we've got standard deviation, so I'm going to put those down. And it says that it's less than 13, and the one that, remember H naught, it gets the equals to. So that has an equals to. The H1 has a less than, and it's going to be less than 13, while H naught is going to have the equals to, so that's going to be equals to 13, because that's kind of, this is the other option we have here. It's either it is 13 or it's actually less than 13. And we also know that the alternative is the claim, because that's what it says right at the beginning. It says test the claim that, and so we know that this must be the claim. Alright, up next we need to identify if it's left, right, or two-tailed. We just need to look at the alternative here, and we see that we are looking at a less than. The standard deviation is less than, so this means it is a left-tailed test. And we could even point to the symbol to make that really clear. Up next, we need to determine the distribution to use. So do we want a t, a z, or is this a chi-squared? And looking at this, we are dealing with standard deviations. And so that is described by a chi-squared distribution. Alright, so since we're using a chi-squared distribution, we're going to need the chi-squared formula. Now that formula is simply chi-squared is equal to n minus 1 times s squared over the population standard deviation squared. So in order to use this formula, we're going to need to identify these different variables. So we have an n that we need an s, and we need a standard deviation. So right here, we're going to run off of our null hypothesis, and it says that it's 13, so that is our sigma. Our sample standard deviation comes from the sample we did right here, and that turned out to be 14. If we look right here, it says that the 13, if a sample of 10 years had a standard deviation of 14. And so that came from our study, so that's going to be 14. And the n is the sample, the number of samples. So we had a sample of 10 years, so that's going to be n is equal to 10. Now all we need to do is plug these things in. So chi-squared is equal to 10 minus 1 times 14 squared over 13 squared. Now we just type this into the calculator. So in the calculator, we're going to turn it on, go to the F1 menu to type a fraction, so alpha F1. And we're going to put parentheses, 10 minus 1, that's just 9. So we'll just do that one. And then we have 14 squared and 13 squared. And we just hit enter. It gives us an answer in fraction. We're going to go back to that F1 menu. So hit the green key and then the green F1 right here. So this y equals 2 button. And go down to number 4, fraction to decimal. And we get a chi-squared value of 10 point, what do we get? We'll round to 2 decimal places, 4. So that is our test statistic. And we've got what we need here for the distribution. So the next step is to actually draw the distribution and see how things play out, and also find a critical value. So we're going to go ahead and come down here and draw a chi-squared distribution. Chi-squared distributions are not symmetric. They're a little different. And we have 10.44. That's going to land, somewhere on this distribution. I'm going to put it right here. 10.44. And we also know that our level of significance alpha is 0.05. So 0.05, and we are doing a left-tailed test. So 0.05 is going to be right here. And this area is 0.05. Now, chi-squared tables actually shade area to the right. So if we want to find the critical value on the chart, we actually have to do 1 minus 0.05, and that is going to be 0.95. So when we look it up, we're actually going to look this up as the area, because the chart's going to tell us area to the right. So if we want to reach this value here, we need all the area on this side up to this line, which is going to be 95% of the curve, because that's going to leave us with 5% left over. So that's the thought process there. It's just 1 minus that. And let's go ahead and look this guy up. So you're going to go to your chi-squared table, and we're going to look up 0.95. And oh, we need a degree of freedom. Our degrees of freedom, well, our n was 10, and the degrees of freedom is 1 less than our samples. So our degrees of freedom is 9. So we're going to look up 9 at 0.95. So we go to the chi-squared table. Yours may look a little different, but it works the same. Here is 0.95, and here is 9. So we're going to go to where they match, and we see that 3.33 is where they match. So we're going to go back to our table, and we put down, this is 3.33. All right, so if a value is smaller than 3.33, then we are definitely going to reject the null. But here we see that we landed outside in the safe region. So the null hypothesis is looking pretty safe. So the next step, at least for Punselin's class, is he wants you to clearly identify the critical value and the test statistic. And so our critical value is 3.33, and the test statistic, test stat, is the one we calculated at 10.44. And of course, this is shown by the formula, but we're just showing that, hey, we know that this is the test statistic, and this one came from the chart and is our cutoff value that is related to our level of significance. So this is the critical value. It's the deciding value. If something's bigger or smaller than it, that's going to determine whether or not we reject the null or if we do not reject. All right, so now let's actually make our decision here about the null hypothesis. So we landed in the unshaded area over here at 10.44, which is very, very safe. So we fail to reject the null hypothesis. So that's what we do with that one. And finally, we need to state something about the claim. So our claim was the second one. And here, we didn't reject the null hypothesis, meaning we thought the null hypothesis was correct. We have evidence to support this, which means that we did not produce evidence to support the claim. Remember, we have to talk about the claim. So we didn't think the alternative was correct, and the evidence we produced doesn't support it. So what we would say is, there is not sufficient, sorry if I spelled this wrong, evidence to support the claim. And that's it. That's all you got to do. It's not too bad of a test. Some people I know get scared because it's a little different. It's area to the right for the critical value. And if you're used to using the calculator, formulas I know can be a little intimidating. But that's all you got to do. If you have any questions about this, let me know, subscribe, and we will catch you in the next problem.